Good morning, everyone. My name is Jeremy Hynek, and welcome to today's webinar. I also have on the line with me today David Wiseman, who will be doing most of the presentation. I have Rachel Evans from our UK office, and I have Joe Belen from our US office. We'll all be answering questions during the meeting as well. Today's topic, this is kind of a play on words, terrified of failures. It was just a fun topic, I guess. We work in a lot of different verticals here at Isograph. And over the last 5 or 6 years, those engineers that are having to include costs in their calculations, it's been a really rough time. Prices have been going up. There's been, things going on globally, political landscapes change. There's a lot of different scenarios that are affecting pricing. So it's not just the tariffs, it's other things as well. Prices on things are just going up. And so we've seen a lot of success with people using tools to optimize their costs. And so that's what this webinar is focused on, is how can you use simulation techniques or modeling techniques to optimize your system from a cost perspective, specifically the things that are costing you the most, spares, maintenance time, downtime, things like that. Again, my name is Jeremy Hynek. David prepared most of the presentation today. He has some models and some topics for us to talk through. During the meeting, if you have questions or comments, usually I say use one or the other, but just post them in the comments or the questions dialogue within the meeting, and me, Rachel, or Joe will respond. Just a few quick notes on Isograph before we get started. Isograph, a Peak Avenue company, has been merged with these other products. You may or may not be familiar with them depending on the industry that you're in, but these are all industry-leading products in their own verticals. So there's Plato, which is a risk management software, uses FMEAs and block diagrams to do kind of a qualitative view of the system. IQS is a quality system. There are several pieces in IQS that I've been interested in from the Isograph side. One is the RCA, the root cause analysis. It uses the Ishikawa method, but also some of the Apollo method to do RCA studies, which is quite interesting to those of you that are in the availability workbench field, because those work quite well together. The newest member of the family is APIS. These guys, for those of you that are used to Isograph software, these guys function a lot the same. They use client-server relationship. They can do small scale implementation all the way up to, enterprise type implementation. And then, of course, Isograph. In Isograph, we have basically two sides to our company. One is the analytical side, which is the reliability workbench, where you get things like fault trees that use Boolean algebra, that, the mill standard 1629 type FAMICAs, predictions, things like that. And then the product we'll be looking at today, or David will be using primarily during his presentation. And that's all I have for the introduction. I mean, I was thinking just to get straight into it. David, are you ready?
Yeah, I'm ready when you are.
Okay, I'll stop sharing. You can take over.
Okay, so bear with me a moment. Okay, hi there, everybody. Thanks, Jeremy. My name's David, and maybe some of you have been on these webinars before. But today, as Jeremy was outlining, we'll be taking a look at using simulation techniques to help us improve the costs in a system. And these costs can come from different places, as we'll see. Could come from downtime, of course, but they could also come from things like spare part purchase and storage, labor, and a variety of other vectors, a number of other places where our costs could come from. Now, I'm going to be using Availability Workbench to demonstrate how some of these principles work, using a couple of modules within that application, one of which is RCM Cost, the other AVSIM. Now, for those of you who aren't familiar, I'll talk around a little bit of each of those as we're going along, and how we can use them to solve different problems when it comes to things like costs. So we'll start with RCM Cost, and there are a couple of different kinds of issues that we can use RCM Cost to help us with. Different types of costs, different sources of costs, where we can maybe optimize, improve what we're doing in order to reduce the kind of costs that we're getting. I'm going to open a little example model I built for the occasion. It is this one. Okay, so I'm not going to sort of vouch for the realism of this model. It's just something I've put together to illustrate the way some of these principles work. But to give you some context for what we're going to look at, I'll talk firstly a little about RCM Cost. RCM Cost is, like much of Availability Workbench, a simulation tool. It's a tool that allows you to simulate failure, repair, and maintenance, almost as if they're happening in real time. The purpose of this is that you can, for example, optimize the frequency with which you perform maintenance. You could simulate what would happen if you did your maintenance once a week, or every 2 weeks, or every 3 weeks, and so on. And the program, based on the information you provide, can make a recommendation. Okay, based on the cost of your downtime, the cost of your spares, it looks like you're best off doing this maintenance every 3 months. We'll see an example of that shortly, but that's at the core of what RCM Cost can do. The framework for that is a functional location hierarchy, like the one you can see on the left here. Those of you familiar with the process of RCM may kind of understand the structure that we're looking at here. I have a little block here that I've created, which represents a part of a conveyor system, a roller. Beneath that is another little block that just represents what that piece of equipment, what that asset does, the function. So I identify the function of that asset. Beneath that, I've identified the functional failure or functional failures that that asset might undergo. So its function is to keep the belt moving. And one of the functional failures is that the belt stops moving. Could be other functional failures, like maybe the belt continues to move, but too slowly, or maybe the movement is uneven. Maybe the belt starts jerking and sort of throwing things off to the side. So there's different functional failures potentially. Again, I'm just focusing on one very simple scenario. At the bottom, we have the cause or causes of that functional failure. Maybe it's a bearing jam or a bearing failure. And we need maybe to replace those bearings in the event that they fail. So like I said, I'm not going to claim that this is going to be the most realistic example in the world, but hopefully it gives you an idea of the sorts of things that we can deal with. So in order for the program to simulate this problem, we need to provide the program with information about that problem. Firstly, how often does it happen? I'm going to open this object up, just double click on this little pause, and I can tell the program about how often I expect this problem to occur. So this could be something as simple as a mean time to failure. See a previous webinar for more information on that. But we can also tell the program in a little bit more detail what kind of behavior we expect. In my example, I'm saying that the average life of a bearing, if I were to do no maintenance at all, if I were to just run it to failure, would be about 1 month. And doing this in hours, by the way. And I've set a shape parameter here, a value that simply indicates that the failure rate of a bearing increases as time goes on. Bearings notoriously tend to wear out, so their failure rate increases as time goes on. And that can be represented by a beta value, a shape parameter greater than 1. I'm not going to give you a maths lesson, but just for a bit of background, that's the average life of a bearing. This indicates that the failure rate is going to go up with time. This thing wears out. The longer I run it for, the more likely it is it's going to jam or explode or something. So I can tell the program about how often failures occur and whether or not there's any kind of wear out happening. So this is what the program will use to simulate the failure. But I can also simulate the maintenance. I can simulate what I would do in the event of failure. So what is my reactive maintenance? What kind of corrective maintenance do I do? But also what kind of proactive maintenance are we doing as well? So from a corrective perspective, we would, of course, replace any failed bearings. So you can see here, I can just tell the program how long it takes to replace a bearing. That's going to be important when we start dealing with the cost of the outage as well. So bear that in mind. I can say how long it takes to fix this problem, and of course, specify any resources that are required to perform this task. Now, I'll look at these a little bit more closely later on. For the moment, I'm just saying, if I need to replace this bearing, I'll need 2 maintenance engineers to do the job and a couple of new bearings to replace that old roller. I can also, as I mentioned earlier, tell the program about any proactive maintenance, any scheduled maintenance that I might be doing in order to prevent a failure from occurring in the first place. And of course, we lubricate our bearings. We give them a squirt of oil to stop them from wearing out. So I can just represent that as a scheduled maintenance task, specify how long it takes, any costs associated with it, any resources required, like the people who do the maintenance. Crucially, I can say how often that maintenance takes place. Without digging into all of the knobs and bells of how this works, this maintenance task will essentially reset us to the beginning of our failure rate curve. So remember I said that the average life of a bearing is about 1 month, but it sort of wears out as time goes on. By doing this maintenance, we sort of push ourselves back to the bottom of that curve. Doesn't have to be that way. It is possible to have a sort of partial improvement where we say, okay, maybe the bearing is 50% or 70 or 80% better. For simplicity, I'm just assuming good as new after I do this maintenance. Again, not vouching for realism here, just a nice simple example to show how things work. So I can say what the costs, what the resources are that are required, any delays that are involved in doing that maintenance. Now, of course, we do also need to think about what the impact of the failure would be, because of course there are costs associated with correcting a failure and there are costs associated with preventing a failure. The failure itself can lead to wider impacts, and I can elaborate on those through the effect feature. Here I can tell the program what the costs would be of an outage. So here I've got this loss of production effect. I'm going to take a little look inside there. And here what I've told the program is that the cost of an outage is just $1,000 per hour. There are other values I could set here. I won't go into huge detail on those. Again, we're focusing on cost for today, but you could do a cost per occurrence, an immediate financial impact of failure. I'm choosing to go purely based on cost per hour while the failure persists, because remember what we said earlier, we can specify how long it takes to perform a corrective maintenance task. We said it takes 6 hours, and for every hour that failure continues, for every hour that we need to spend fixing that problem, our costs go up by $1,000. So obviously it becomes important to fix those problems as quickly as possible, or preferably prevent them from occurring altogether. That's a little background on some of the information that goes in. Like I said, if we want to simulate failure, we need to tell the program how those failures behave. We want to simulate maintenance and repair. We need to tell the program about what the impacts are of those different maintenance tasks, what resources are needed, and things like that. And if we want to simulate the cost of our outage, we need to specify what the effect of a failure would be. And that's what we've done. What I didn't do was look closely at those resources, because remember, for example, if there's a failure, we need to replace the failed asset, replace the failed piece of equipment. We're doing that here. We've got a maintenance engineer. We'll need 2 of those guys to do that. And we can, of course, set things like the cost of calling this person out and any delay associated with getting them to the scene. So all of those things can be factored in. Again, I'm keeping it very simple for my example. But most important, I think, for the purpose of this demonstration, I think, is going to be the spare, because the whole sort of central theme of today's webinar is to do with, the financial impact and other impacts of things like tariffs and customs. As it gets harder and harder to import and export, these things are going to have an impact on our day-to-day costs. We can look at ways in which we can mitigate the impact of those costs using software like this. So if we have a look, let's say to buy a new bearing, it's a pretty cheap little thing. It's $140 for a new bearing. And, maybe I'm just keeping 10 of them to hand. So I keep 10 bearings in a crate or on a shelf somewhere. And it costs me $1 an hour to store them there, because I need to sort of keep an eye on them and keep them dust free, and maybe even keep them lubricated in situ so they don't dry out while they're waiting to be used. And it maybe takes me an hour to send someone to the cupboard and pull one out and bring it to where it needs to be in the event of a failure. This is where I'm storing my spares. And in the event that I need a new spare, I can ask the supplier to send me a new one, and maybe 48 hours later, I'll have my nice new shiny bearing to go into storage or to use in my system. Maybe I'm importing them. Maybe I have like a good, reliable supplier overseas, reasonable price. They can get me new bearings in about 48 hours, which is pretty good. So yeah, that's all set up. And maybe another couple of things that are worth taking a look at. I'll hop into the options for a moment, and I'll take a look at the lifetime, where I'm going to say, I'm looking at the life of this system over 20 years. So I can set a time horizon, essentially, for my system. So I'm going to look ahead for 20 years, base my predictions, base my recommendations on that. Time intervals, I'm going to break the life of my system into 21-year intervals. That will be useful a little bit later. Maybe I'll leave it there for now. But I'm also going to tell the program that I want to do 1,000 simulations. We are doing Monte Carlo simulation. Again, I'm not going to give you a maths lesson, but basically, Monte Carlo simulation works by generating random numbers and using them to sample a statistical distribution, and in so doing, simulate a real world process, because all real world processes are based on statistics in some way, up to and including the failure of assets. We use something like a variable distribution, as we've done here, to mimic the behavior of a failing bearing, and we use random numbers to generate simulated times to failure. And in order to get a representative value, an expectant, a good, what was the best way to put it, expectation value, a prediction that is representative of what we can really expect to see, nothing too outlandish, we would need to simulate as many times as possible. So what this means is that every time we simulate the life of this system, we're actually going to simulate those 20 years 1,000 times. And the result we see at the end will be the average over those 1,000 20-year lifetimes. This is the way that Monte Carlo simulation works. The more simulations you can do, the more statistics you can build up, the more reliable your result will be. I could probably do more simulations than this, but I'm keeping it quite low so my results come through much more quickly. But this should be enough for the purposes of our webinar today. So keep that in mind. When we run an analysis of those 20 years, the program is actually doing it 1,000 times to give you your average expected result at the end. Okay, so we've got our little model. And maybe the first thing we want to think about is how can we improve the cost by improving our maintenance? Now, there are a couple of ways we can approach this through the interface of the program. I'm going to use the strategy tab for the failure. So I'm going to open up that failure, hop over to the strategy tab. And the reason I'm doing it this way is because it will allow us to have a little conversation about cost benefit ratio. So as you can see, I'm doing my planned maintenance once a week. That's 1 week in hours. So every week I lubricate the bearings and things seem to run pretty smoothly as a result. But I can simulate this failure. I can do 1,000 20-year simulations of this failure pretty quick, as you can see, and I can get predictions of things like cost, the amount of downtime due to failure and maintenance, and so on. But the thing I want to focus on here, like I said earlier, is the cost benefit ratio. This is the ratio between the cost of this failure if I do the maintenance as I do today, so basically this value, and the cost of this failure if I simply run to failure with no maintenance at all. And it looks like if I do this maintenance, my costs are only about 28% of what they would be if I did a run to failure strategy instead. Just to illustrate that, you'd probably expect this to go up by almost 4 times if I did no maintenance. If I do this and run it again, you can see it does. It increases by almost a factor of 4 as a result of doing no maintenance. So case in point, you can see doing the maintenance is much better. And we get, and the cost benefit ratio is a nice number because it gives you an idea of just how much you're saving relative to what would happen if you just did no maintenance. So straight away, you have justification for doing maintenance and not just letting stuff fail and replacing it on the fly. But of course, maybe we could push this number down further. The lower this is, the better. How can we do that? Well, we can ask the program. Ask the program what is the best frequency with which to perform this maintenance. So I'm going to do an interval optimization for this task. I'm going to say to the program that I would like to try 30 different potential maintenance intervals at increments of 24 hours. What that means is the program is going to simulate this failure with a maintenance interval, with a lubrication interval of 24 hours. Then it'll do it again with an interval of 48 hours, and again with an interval of 72 hours, and so on. So we'll basically try every possible interval from 1 day up to 1 month, and hopefully tell me what's the best frequency for doing this maintenance. So let's give that a try. It looks like it's suggesting that actually I could be doing this maintenance every 10 days instead, leave an extra 3 days between lubrications, and perhaps save some money as a result. So I can accept that recommendation. You see it updates the interval. Run again, and you can see the cost benefit comes down as a result. Only a couple of % of the cost of run to failure, but you can see there how the program can make recommendations to help you improve the cost as a result of maintenance. As you can see from this plot, if you were to do the maintenance much more frequently at a lower interval, high cost because you're over maintaining. A longer interval, means that you've got less maintenance and therefore more failures, and you get high costs again as a result. The program is just helping you find that kind of sweet spot where the interval gives you the lowest possible cost. So that's, again, very good. We've got a nice maintenance interval. Another thing we could do is optimize the number of spares that we keep in storage. We've asked the program how often we should do maintenance. Maybe we could change the number of spares that we store, and that would help us to improve our costs too, because it can be expensive to store spares, but it's also expensive waiting for new spares to arrive if you run out. So what's the best balance there? What's too many spares and what's not enough? Same principle applies. We can ask the program to try out different numbers of spares in storage. I'm going to try between having no spares and having 30. Everything from 0 spares in storage up to 30. I'm going to run that. And there you can see the program recommends I keep 8 spares in storage, so maybe a couple less than what I'm already using. If I store more spares, I have high storage costs. If I store fewer spares, I start to get higher and higher unavailability costs, because there's a chance I'll run out of spares. And if there's another failure, suddenly I'm having to wait 48 hours for a new spare to show up. So getting that balance right can be really important. And the program is suggesting 8 spares in storage. And again, I can accept that recommendation, and that will just update my spare. But in many respects, everything I've shown you there is really just background for the big thing we want to talk about today, which is unexpected increases in cost and red tape as a result of political changes around the world. And let's save this model. I'm going to click save. And for a bit of fun, what I'll do is I'll change the name of this model, and we're going to call it Tariffs. Nobody seems to remember. Well, I certainly can't remember how to spell it. Is it 2 R's or 2 F's? I think it's 2 F's. And then I will file, save project as, and again, I'm just going to give that a new name. So I've now got 2 copies of this project, and this project is going to represent worst case scenario. Suddenly, our spares have become more expensive. I'm going to go into the bearing and say, well, okay, maybe the cost of these objects has gone up by about 50%. That on its own, compared to the costs of other things that are going on in our system, isn't really very much. Other bigger assets may have bigger issues, but for something small like this, it might not be, maybe another $70 is not that big of a deal. But often these problems come not just with a cost impact, but with an impact in terms of red tape, the amount of time it's now going to take to get these things through customs and so on. So maybe now, instead of a nice quick 48 hours, it's going to take a week to get these spares from the supplier, getting them through customs at the border and so on. All these things can, of course, have an impact. Well, maybe we can mitigate some of that impact by optimizing the number of spares we store again. Let's have another look. More expensive spares that take longer to get hold of. Should we make any changes? And the program seems to think, yes, maybe you'd be better off keeping more spares in storage. And again, that kind of makes sense. If it's going to take a week to get more spares, it's safer to have more of them, because you're in bigger trouble if you run out, if it's going to take that long to get more spares. So I'm going to save that. And then I could think about an alternative. Okay, so we've been importing our spares and it was working for us, but now we're in a position where importing is a bit of a struggle. We can store more spares, but maybe there's an alternative route that we could take. What if we went for a domestic supply of spares? Perhaps they're more expensive for various reasons, but they're nearby and there's no red tape involved. Maybe that's a direction that we can go. So I'm going to do the same thing. I'm going to create another copy of my project. I'm going to call this one domestic because I'm getting spares from a domestic supplier. Oops, I've overwritten my tariffs one. That's fine. I've got another copy of that. So I'm going to call that, what am I going to call it? Domestic. And yeah, so now I can go into here and I can maybe say, well, okay, I can get spares from a domestic supplier. They're a bit more expensive, but on the plus side, they only take 24 hours to arrive instead of 48 or a week. So again, I can run that model, see what the recommendation is. Now it's saying, in this case, you can store just 6 spares because the impact of a delay on getting spares from the supplier, not as great. We can afford to store like maybe a few fewer spares. So we can accept that recommendation. So we've now got 3 versions of this project. One where we just have tariffs, where we just have a regular import without tariffs. Another where we have tariffs applied and an additional logistic delay. And then another with a lower logistic delay, but domestically sourced spares, which are a little bit more expensive. So let's take a look at how these different models compare. So I'm going to open the import version of my model, and so let's see. Is this on up to date? So no, I'm just going to quickly run that through again. Okay, and I will run that. And what I want to do is once I've got nice optimized spare parts is just run a lifetime simulation of this model. So I've got the lifetime cost stored. So there's the total cost of this model, including all the spares, including all the downtime, labor, and so on. So I'll save that. Then what I'll do is I will attach as libraries other versions of this project. I'm going to make sure I don't have any other libraries attached first. Yeah. Then I will attach the import plus tariff version of this model. And I will attach the domestic version of this model. I'll go to the plot view, and I'm going to take a look at the project comparison plot. So this is allowing me to compare the total cost of each model side by side. And I'm going to tweak the display of this a little bit. So I'm going to ask the program first to stack those things up, stack the bars up to make them easier to compare. Maybe show a grid as well. So I can see pretty much, it's tricky because the bars are quite long relative to one another. You should be able to see that import is the cheapest of the 3. So if we're just getting our spares at the lower price with a relatively short delay, that gives us a lower cost. Fair bit more if we add the tariffs and the additional delay, get more cost as a result. Domestic, okay, the cost drops a little bit. Probably just about see that. The cost falls a little bit, but it's still not quite as good as it was earlier before the tariffs were applied. There is another way we can view this as well. I could change this so that I look at a cumulative cost profile. maybe you remember earlier on, I showed you where you could set the system lifetime for your project, tell the program what the time horizon is for your system. And we set it to 20 years. But we also told the program that there were 20 equal intervals as well, that we were breaking the life into 20 equal 1-year intervals. There are a couple of purposes that this can serve, but the primary one is for when you're plotting things like cost against time, because what the program is going to do is show us what the cost is in each year, and what this adjustment to our project comparison plot will do is allow us to compare the cost after each year, the cumulative cost after each year for both models. And it might become a little clearer then how these models perform against one another. So you can see here, year on year, how the domestic, import, and tariff versions of the model compare. And the clearest indication of that is with the final year. At the end of that year, you can see tariffs, the most expensive. Obviously, the original import without tariffs was the cheapest. And in the middle, you've got the domestic version of our model. So what we can kind of take away from this is that we can use these simulation methods to test out different scenarios against one another. So initially, we can do things like optimize our maintenance, determine how frequently we should replace or lubricate or clean in order to reduce our costs. So we're not over maintaining, but also we're not under maintaining. We can also use these methods, use simulation to determine things like how many spares we should store, so that we're not storing too many spares and paying high storage costs, but at the same time not storing too few and risking high downtime because we're having to wait for new spares to come from a supplier. And you can then use that to help you to deal with sudden and unexpected changes in circumstances. The example we showed here, okay, well, suddenly we've been hit by tariffs and red tape. What impact do we expect that to have? Hey, it looks like that's going to make our life a lot more expensive. What can we do about it? What other scenarios might help us to absorb some of that impact? Here, what we found was that maybe sourcing domestic, more expensive spares is suddenly cheaper than getting sort of spares imported and having to deal with the red tape and the increased cost and so on. Maybe there are other things you could try. The tools like this will allow you to try all kinds of different scenarios against one another, different types of maintenance that might reduce your dependence on spares, things like that. Now, RCM cost as a tool tends to be very maintenance focused. As a result, it treats individual failures as if they are largely independent of one another. So you would list out the failures that a system might undergo, and you would devise your maintenance and sparing strategy for each one. You can group them together, but there's very little in the way of interaction between individual failures, which is fine if you're dealing with, say, mining equipment, which is largely one thing independent of another. My conveyor belt is a separate thing from my trucks and so on. What if you're dealing with a more integrated system? Maybe it's a process, for example, a system where the failure of one asset could have a very real impact on the failure of another, where the failure of an asset might not necessarily cause a complete outage of your process, but might cause a degradation. Using a functional location hierarchy like that in RCM costs wouldn't really work for us. What we could do is build a RAM model, like what we find in the AVSIM part of the tool. So let's leave our RCM cost project there. I'm going to close up my libraries again. And let's take a look at a RAM model, only a very simple one. So now we're in the AVSIM part of the tool. This is the part of the tool that is dedicated to RAM modeling. And as you can see, now instead of dealing with individual, mostly independent failures, we can build a reliability logic diagram that represents the interaction between the outages of different assets. Here, I've got these 4 blocks in parallel, perhaps representing different hoppers on a production train, each one of which can carry 25% of my system throughput. Much like in RCM cost, each of these blocks can have failure, repair, and maintenance data attached to them, so I can simulate their failures. Just the difference now is, I would say, well, if this one goes down, my system is still available, but perhaps at a degraded 75%. So that information is here in the failure model that I'm using for each of my blocks. Here I've kept it quite simple and just put in a simple mean time to failure. I think that's 30 years if I remember correctly. So quite a long lifetime for these things. They generally don't seem to wear out. They have pretty much a constant failure rate. On average, they last about 30 years. Again, there is maintenance associated with them as well. So let's run our model, and we run the model. And of course, with a RAM model like this, primarily we're looking at things like downtime, productivity, and so on. Here you can see I'm not getting any downtime. I have a lot of redundancy, so that's maybe kind of expected. I've got 4 pieces of equipment in parallel, and each one has an average life of 30 years. The possibility of all of them failing at the same time at some point in the space of 50 years is very, very small. So I'm ending up with an average total downtime of 0. What I do see is that my average capacity is a little bit below 100%, because from time to time, one of my hoppers might fail. I lose that little bit of production, and I end up with production costs as a result, or rather production losses as a result. These come through from the consequence that I've associated with this system. Got this consequence here, where I've specified what the cost is of losing 1% capacity per hour. So for every percent per hour, there's a cost of $100. So what that would basically mean is if I lost one hopper, that's going to be about $2,500 per hour because of that 25% production loss. And again, just like we kind of did in RCM cost earlier, we can specify any spares that we need. One of these big hoppers is a bit more expensive than a bearing. I'm going to say about $8,000. And again, it's going to take maybe 48 hours to wheel in a new one in the event that we need it. But again, maybe there's going to be a big problem. Tariffs are coming in. Now, instead of $8,000, it costs $10,000. And instead of waiting 48 hours, we're going to be waiting for 168 hours, 1 week for a new hopper to arrive. So of course, that's going to make a big difference. So I can run that, and we're going to get those results through, and naturally there'll be higher costs for our spares, higher costs for our downtime because they're having to wait longer for spares to come in. So I'm going to save that. Then what I'll do, just like before, I'm going to create a separate version of this model. I'm going to call this refurb, because there is another kind of strategy that we could pursue with our spares that might help us get around some of these costs, some of these additional downtime from spares becoming more difficult to acquire. So I'm going to save that as refurb. What we can do is we can go into the spare and we can set up a repair shop. We can tell the program that actually in the event that one of these hoppers fails, there's a chance that we might be able to fix that broken hopper and return it to storage as if it's a new spare part. Now, obviously, these things can't be done for free and it takes time. Maybe that's why we've never considered it before. But suddenly, with these tariffs coming in, we've got this sudden motivation to consider other options. So let's say that if one of these hoppers fails, we can pull it out. We're going to try and repair it and return it to level 1 storage as if it's a new spare. And that the cost of doing that would be $2,000. Average repair time, maybe this thing has to spend a week in the shop before it's ready to be wheeled back into storage again. And maybe 75% of hoppers that fail basically have to be scrapped. But the remaining 25% we can fix and use again, recycle them, use them again in the future. So I'm going to run that model. I'm going to save that. And just like I did before, going to attach my original hopper model and do a project comparison. And as you can see, again, just from the grid in the background, my refurb model is coming in with a lower cost than my reorder model with the added tariffs and the added delay times. And, again, if we wanted to, we could display that a different way. There's a cumulative cost profile, and you can see pretty clearly there that the reorder cost or the reorder model has a higher cost than the refurbish model. So again, we get an idea of how these simulation tools can allow us to try out alternative scenarios and see what else might work. So like I said, we've seen that we can optimize our maintenance, improve the frequency of our maintenance, or even try out entirely different maintenance strategies, something we didn't really look at. We were looking at lubrication of a bearing. You could alternatively, instead of doing proactive lubrication, do an inspection and only lubricate if the inspection indicates that it's necessary. You could install a condition alarm, model that, and see, something that maybe alerts you in the event that lubrication is required, and you can come out and do the job, or even it maybe even happens automatically. You can build these things into models, compare the outcome, see which methods are predicted to work the best. And those same principles work with spares as well. So how many spares should you store so that you're avoiding additional costs from having too many or not enough? How do you respond to sudden changes in the cost of spares and the availability of spares? Do you store more? Do you store fewer? Do you look for an alternative source of spare parts? Or, as we saw just now in AVSIM, could you try recycling them, refurbishing spares and returning them to storage rather than buying new ones wherever possible? So simulation gives you the ability to try out these different scenarios, these different potential strategies in the safety of a desktop simulation without the need for an expensive pilot where you're just going in blindly and hoping that it works. You can just pop the information into a model, run it, see what the predictions are. Naturally, the reliability of those predictions is dependent on the quality of the data, which is a whole other webinar potentially. But even with relatively simple data, as we've used here, you can still get useful representative results to help you to make those decisions. So that kind of brings me to the end of what I was going to show you today with simulation, with optimization and availability workbench, which gives us maybe 5-10 minutes, I think, to deal with any questions or any further points of discussion. So yeah, Jeremy, did you want to step back in? Did you have any questions from the chat
Yeah,
or?
I have a question, David.
Yeah.
How would you address things like inflation? So you have things like tariffs, lead times. How
Hmm.
would you do like a universal increase of in something like inflation?
Yeah. So yeah, that's true. So in the models, the systems we've looked at here, we've had sort of quite long lifetimes. Our bearing example, I used a lifetime of 20 years. So like a time horizon of 20 years. With this model, I'm using 50 years. These are quite long periods of time, and things change. The cost of some things inflate. The value of a system itself can actually go up over that time as well. It can appreciate in value, as can your product. And these things, these inflationary and value-based forces can have an impact on the overall cost. And it can be worthwhile then to adjust the predicted cost from your model. I guess you could say you're adjusting it to today's money, essentially. So as time goes on, you're accounting for inflation in the final result that you show. Now, the program can do that. If we take a look in the project options, and this applies both to RCM cost and to AVSIM, there is a net present value tab. So I can turn on this NPV, net present value calculation, and I can apply, first of all, a percentage yield. So I might set that to, say, let's say 2.5% as an example. What this means is that as the value of my system and its product increases over time, I can discount a certain percentage of my cost per interval. What do I mean by interval? Well, for anybody with a good memory, you might remember I said earlier that when I set the intervals on the lifetime tab, I said it primarily deals with cost plots, but has other functions as well. This is the other function. That discount from your costs will be applied after each interval, in this case, every year. So I'm saying I'm discounting 2.5% of cost per year. But at the same time, other things might be getting more expensive. Maybe your labor costs are going up by a certain percentage per year. Maybe your spare part purchase costs are going up by a certain amount per year, and so on. So all of those things can be factored in, so that when you run your model, what you get at the end is what we call an NPV, a net present value cost, a cost adjusted for inflation, for the increasing value of your system, things like that. And again, these things can be quite important when a system has a long lifetime and the value of money and the value of resources changes over that period.
Okay, perfect. Oh, can the number of workers, maintenance workers on a shift be modeled? Can you model the number of employees you have working on maintenance?
Yeah, so this is something that is specific to AVSIM, because RCM cost treats individual failures as being independent of each other. The number of people you have on site isn't really taken into account there, because you can't run out of people because they're all working on one thing or another, because everything's treated individually. In AVSIM, though, if you're setting up your labor categories, the people who do the maintenance, you can say, okay, this is how many people I have available to me, 1, 2, 10, 100. And during the course of the simulation, if you ended up in a situation where everybody was tied up, everybody was working on something, and another task came up that needed to be done, that task would have to be queued in order, and it would only be done once someone or enough people became available. The nice thing about the way AVSIM handles this is that you can actually look in the results for individual assets, individual blocks in your system, and it will tell you how long it spent queuing for different things. So if a piece of equipment is experiencing an inordinate amount of downtime because it's waiting for people to show up to do maintenance because there's not enough of them, then that could spur you to consider bringing more people on site or hiring contractors to do some of the work to make sure that your personnel levels are sufficient.
Oh, perfect. Thanks, David. We just have a couple of minutes left. So I'll take over really quick, just to show a couple things. So today we've been looking at the availability workbench software. So David covered AVSIM, RCM. Both of those products include Wiseman. There's a life cycle cost that we did not get into, which a lot of the life cycle studies regarding spares and maintenance are in AVSIM and RCM cost, but a life cycle cost lets you add unique calculations. For example, we had a client recently that wanted to know how much he was going to spend on fuel over the life of a system. So that would be an example of where you'd add life cycle cost. You can basically add anything into the studies using life cycle cost. Process reliability, it's a good view of how your system's behaving over time, whether it's getting better or worse. And then we have some portals into CMMS systems like SAP and Maximo. Accelerated life testing, it lets you put these systems under increased stress to see how they behave, so you can predict a lifetime value. We have APIs and plugins so that you can link to outside programs, and there's an enterprise add-on which lets you save files in a central location. It gives the admin control over who can access those files and what they can do with them. And just in conclusion, my name is Jeremy Hynek. Thank you for attending today's webinar. You'll be receiving a follow-up email with feedback. I would love any feedback people are willing to give. Ideas on future webinars, any questions you had from this webinar. You also have access to David and Joe for training or consulting on your individual systems. We can always step in and help wherever you may like. And that's about it. Thank you for attending today's webinar. I look forward to hearing from you and watch for future webinars from us as well. Okay, thank you.